Our next speaker is Yang Li. He is an associate professor from the Department of Computing at the Hong Kong Polytechnic University. His research interests include the backscatter and wireless communication systems, mobile computing, and indoor localization. So, Yang, please.
Oh, okay, thank you. But I needed okay.
Are you connected?
Yeah, I needed the audio. I have the audio to play. I don't know if I.
It should play directly.
Okay.
Switch display. Oh, good.
Okay. Thanks for the introduction. It's our great honor to introduce our research advance. And I'm Lei Yang from the Hong Kong Polytechnic University. This is our work, empowering smart buildings with self-sensing concrete for the structural health monitoring. In the last year, a 12-story beachfront condo in Miami partially collapsed, resulted in a tragedy of 98 deaths. Okay, this accident shocked the whole world, but actually it happened each year in the past decades. Concrete architectures inevitably suffer from the aging and the environmental degradations. So the best approach to preventing buildings from collapse is to conduct the structural health monitoring, SHM. In the field of the civil engineering, currently four sensing solutions are currently employed. The first is that we can implant the optical fibers into the concrete, and when the light transmitted along this fiber can be used to detect the temperature, humidity, and the stress. The second approach is that we can use the electrochemical sensors. Okay, so the potential difference can be measured using the two electrodes. One is connected to the inside, another is connected to the reference. And this sensor can be used to measure the mechanical composition. And the last one is PZT, right? We are very familiar. We can deploy the PZT sensor into the concrete and use the cables to get the sensing data out. Unfortunately, these three solutions widely used currently suffer from the wired connection. It means that we cannot deploy them everywhere because we must use the wires to for the power supply and the sensing connection. Of course, RF-based wireless sensor network is a promising solution for the SHM. We can deploy them on the surface of the building. Unfortunately, it's rarely used in practice for two main reasons. The first reason is that the sensor are battery powered, so we cannot implement them into the building because it's hard for us to take them out for the battery replacement. The second difficulty is that the water and the fiber of the concrete naturally forms a Faraday cage, which prevents our signals from being out. Okay, so these existing solutions have the many limitations: intrusive, high cost, wired connection, or limited coverage. In the recent years, architecture experts envision the self-sensing concrete. Conventional concrete is mixed with the minor functional failures to construct an interchangeable and sensible wireless network. And in this work, we push this vision forward by introducing a battery-free, cost-effective, computable, sensible failure. We call that as an eco capsule. Okay, as a part of the concrete, And the e-capsule's nodes are mixed with the water, the sands, and other raw metals together during the building construction. They will be implemented into the building permanently without any follow-up maintenance. And meanwhile, we use a radar to transmit the ultrasound for the power supply and the communication. Okay, actually, our eco capsule is kind of the PAB, piezo or acoustic backscatter. Unlike the previous PAB systems, they are used for the underwater communication. We use the PAB for the communication in the solid materials. To better understand our ideas, I will show a very short video.
Given the increasing number of building collapse tragedies nowadays, people gradually recognize that structural health monitoring becomes indispensable for civilian buildings. We present EcoCapsule, a battery-free and implanted piezoelectric backscatter node, to harvest energy and sense concrete health information to the outside. The outside reader sends continuous vibration to the concrete via a piezoelectric transducer. The EcoCapsule can leverage the PZT again to convert the mechanical vibration to electricity and use it. For backscatter, the EcoCapsule can change the short and open status of the logic switch to reflect or not reflect the incoming continuous wave. We fabricate the prototype of EcoCapsule, which contains shells, a printed circuit board with sensors, and piezoelectric transducers. The PCB is about the size of a $5 coin. Multiple sensors of structural health monitoring can be mounted to the PCB and transmit data to the outside. It is easy to be assembled and deployed. Different shapes of EcoCapsules are also designed for withstanding high pressure or reducing the volume. We cast the EcoCapsules in normal and ultra-high-performance concrete, which holds the record for the strongest concrete in the world, for testing. The wave prisms are also fabricated to eliminate P waves. We can observe the implanted EcoCapsules via CT scan. For the downlink PIE encoding-based signal, we leverage frequency modulation to simulate amplitude modulation to suppress the ring effect. After harvesting enough energy, the EcoCapsule can start to control the logic switch to backscatter. Not only the ID information, but also the concrete health monitoring data can be delivered to the outside. We envision this revolutionary technique could bring safe and smart buildings to the world.
Okay, this is our idea, engineering a PAB system for the self-sensing concrete encountered many challenges. The first challenge is that how can we wirelessly charging the encapsulates without knowing their positions? Imagine that a large number of the encapsulates are deployed into a wall without knowing their position. But now we use a PZT to wirelessly power up them with a very limited coverage. Okay, so we notice that the impedance between the concrete and the air differs a lot. It means that most energy, 90% energy of the injected ultrasound will be reflected at the boundaries. So inspired by this fact, we can use the reflections to power up all the nodes, even we don't know their positions. So we inject the ultrasound with a non-zero incident angle using a prism. Okay, so the second challenge is that how to deal with the coexisting multiple modes of the body waves. Okay, what is the models of the body waves? When the ultrasound goes across the boundary between the prism and the concrete, part of the energy will continue to go forward as a P wave, and another part of the energy will be converted to another form of the wave. It's called as the S wave. We can simply consider these two waves as the two copies of the original mechanical waves, but they travel in different ways and different speeds. So you can imagine that there is two copies arrived at the receiver, but they arrived at different delays. So they will cause the difficulties in the decoding because there is an inter-symbol interference. So how to deal with this problem? We know that the Snell laws told us that when a wave goes into different go through two different materials, they will be refracted. Okay, so two waves will be refracted, and the refraction angle of the P wave will be greater than the S wave because the P wave travel faster. Okay, this is a formula tells us. And so you can imagine that when we increase the incident angle, both the refraction angle will be increased as well. And when the P wave will forcefully reach the 90 degree, and all the P waves will converted from the body wave to the surface wave. Okay, like this case, right? Okay, so our solution is that we injected the ultrasound with the angle between the first critical angle and the second critical angle to totally remove the P waves. Okay, the third challenge is that how to tackle a ring effect in the downlink. Ideally, PZT should stop the vibration when the power is off. But the reality is that even the power is off, the PZTs will still vibrate because of the inertia. Okay, so you can see that the tailing of the vibration will interfere with the following symbol, causing the intro symbol interference. How can we do that? How can we resolve this problem? So this figure shows concrete the frequency response. We challenge the concrete with the different frequencies. And you can see that. Okay, so the concrete will respond with a higher amplitude at the resonant frequencies and with a lower amplitude at non-resonant frequencies. So that inspired by this phenomenon, we changed the OK to the FSK. We transmit the bit 1 at the resonant frequency, and we transmit bit 0 at a non-resonant frequency. And the amplitude of the signal at the non-resonant frequency will be naturally suppressed by the concrete. So we are not the OK, but use the FSK. But however, on the node side, it still uses the OOK for the demodulation because only detect the amplitude change. So this is we call that it's FSK, but OOK out. Okay, so the last challenge is how to defend against the extremely high pressure. Our node must withstand almost three times higher pressure from the buildings than the underwater PAB systems. To resolve their problem, we made a lot of the efforts on the shelter design. Okay, so the current prototype can support the building lower than 100 meters. It's about the 4 floors. Of course, we can change better or solid materials and support the higher building. Okay, this is the circles of our prototypes. And finally, we give some evaluations about our prototypes. In this slide, the first picture shows that the fabrication procedure, and the second picture shows the concrete we have made. And another is a CT scanner. We use the CT scanner to check the intactness of the nodes. And the third picture shows the X-ray imaging. Okay. And this picture shows the backscatter signals we have received at the radar. We tested our prototypes in the different architectures, such as the slab, bearing the column, and the defensive walls. Okay, this figure shows the charging performance, and distance is the longest distance that a node can be powered up. Okay, so we can see that we can achieve the maximum distance of the 6 meters when giving 250 volts transmitting power. And this figure shows the uplink performance. And we fix the node at the position, And we change the bit rates and measure the SNR, signal noise rate. SNR determines the decoding ability. We hope that we can get a higher SNR. And from figure, we can see that a PAB and U2B are two the underwater PAB systems. And from figure, we can see that we can achieve the higher SNR than other two systems when the bit rate is less than 8 kbps. We also measure the throughputs of our prototype across the different types of the concrete. The normal concrete, the ultra performance, ultra high performance concrete, ultra high performance fiber reinforced concrete. And finally, we can achieve the average, 13 kbps the average throughput. This is downlink performance. I just showed the anti-ringing effect. We can see that when we use the FSK can improve the SNR by 3 to 5 times than the conventional OK. Okay, so finally, we conduct a long-term SHM pilot study on a real-life footbridge since the October 2019. And this footbridge has a length of 84 meters. It's used to connect two campuses of our university. And we totally deployed 3 types, 88 conventional SHM sensors. All these conventional sensors, such as the optical fibers, the accelerators, and also the chemical sensors, such types. And the total cost is up to $10 million if we use these conventional sensors. And we also deployed 6 eco capsules on this bridge to measure the acceleration and the strength. And the cost is lower than the 1K. Okay, so this figure shows the acceleration data collected across the 1 month. And you can notice that there is an exceptional period from the July 16 to the July 25 because the acceleration or the stress changed a lot. Okay, during this time, the Hong Kong was experiencing a typhoon, so that is why we can see some significant changes. Okay, in conclusion, in this work that we introduced a battlefield, a small-sized PAB, and it can be used to monitor the structural health of all the buildings. And we leverage the body waves for the wireless charging and backscatter communication. And finally, we take the pilot study. Thanks very much.
I'll start with a question. So you had to build a bridge to verify?
No. I don't have such funding to build a full bridge. Either full bridge has built earlier, and we just insert some sensors into the bridge.
Okay.
For the structure.
The wall as well. You had a large wall with sensors embedded. Was that built like during the project?
Oh, yes, that's a cooperation with the civil engineering, expert from civil engineers. Actually, the last 2 authors are from the civil engineering. So they have implemented the sensors. We just get the analysis of data, collected data, analysis data as the baseline to compare with our sensors.
Nice.
Okay.
Hi, I'm Venkat from MIT. Really cool work. Can you comment on how many types of sensors you need for the different pressure levels? As in, say, is it one type per 10 meters or something like that?
Actually, I have no idea because it's just a prototype. We only deployed 6 prototypes on the footbridge. So in the future, I think that the size is not small enough. So in the future, I hope that we can continue to reduce the size, and we can really like the size like the comparable to the sand or the stones, so such that we can really mix them with the cement and and pour them into the building. So in my vision that in the future, if we use our technology, that all the buildings will contain the hundreds or even thousands or millions of them because it's very small and very cheap. So that in the future that we can only use the radar to collect the sensing data from the building inside. Okay, thanks for your question.
Other questions?
Yeah, thanks for your talk. This is Bill from UIUC. I'm just wondering, like, have you looked at the topic of like how inserting like that small ball into the concrete would affect the structural stability of the building? Like, you basically like dig a hole in the brick and you have to install something different in it. Do you think that's gonna make the building take like a less maximum pressure, and do you think that will make the building less stable? Thanks.
Thanks very much. It's a very interesting question that the answer is affirmative because we collaborated with the expert from the server engineering. So they confirmed that this says, so currently, right, okay, not in the reality the buildings, but currently that they don't have the seriously negative impact on the building. So yes, I think that is a good question because you can see that in the prototype there is a very large and there's many holes. That might be give some impact on the risk on the building. That's a good question. That is also our future work that we will address. Thanks.
Great. Let's thank the speaker again. Thanks, Yang. Great work.